Hello, Mr. Long. This is FRK number 3, part 8. We are trying to, part 8, we are asked to plot the data points for the quantity given in the data table, right? And so I'm just gonna, oops, the wrong one. I'll bring out this graph, and this is part 8. We're asked to graph below the table above. So we are given the two values fn and t. So for fn, we're gonna put it on the y-axis and t on the x-axis, and the reason being is that the force is determined by the time seconds, and then we can just do 0, 1, 2, 3, 4, 5 because it is evenly separated given to us, and this is at 0, it is at 100 or 100. So we can split this 180, 60, 40, and 20, and 0 here. And it says that time t equals 0. Fn is equal to 100, so we put a dot here. At time t equals 1, 80, 2, 60, 3, 40, 4, 20, and 5, 0. And as you can see, this is a very linear, what's it called? Linear graph or function. And so we can just draw a straight line through all the 5 points. And that's part A done. So for part B, we are asked to, using the information given on the table, you are asked to determine an expression for ft. So we're trying to find ft, and to find ft, we can just use the formula y equals mx plus b, right? Because ft is a function that is determined by t, and what we know is that we can just use a table that was given or the graph, because that is also the force determined by the time t. And using the y equals mx plus b, we know that y in this scenario is f of n, as we stated earlier, and x, the variable, is t. So all we have to do is replace y with f of t is equal to mt plus b. And how do we find b and t? B and n? Let's start with m, where where m is just the slope, right? So how do we find slope? We can just, m is the slope, and what we know is that we already found the slope. We already have it right here, right? And what we know about this graph is that it shows us the slope that every 1 second passes, it decreases by 20 newtons. So it is negative 20 over 1 second. So that is our what is it called? That is our m, and we can just plug that in. F of t is equal to negative 20 t plus b, and here b is we can just substitute in 0 for f of t, right? F of 0 is equal to negative 20. Yeah, well, we can just put negative 20 times 0, which is 0, plus b. But we know that at f of 0, it is equal to 100. So therefore, f of 0 is equal to b, which is equal to 100. Therefore, b is equal to 100. And now we have b and m. So we have the function f of t is equal to negative 20 t plus 100 newtons. This should be noted as newtons over s, and this should be just newtons. And yeah, you should get rid of that. And that is our formula. For part C, we are asked to derive an expression for the acceleration at of the car. So for acceleration, well, what we know is that f is equal to ma, right? And if f is ft, then if there's a function ft is equal to m times a of t. And the reason why a has is the one with the variable is because m is a constant value, and a is already known to have is already known to be dependent on time, right? So what we can do is just ft divided by m is equal to a of t, and that gives us the acceleration formula. And right here, since we know that f of t is equal to negative 20 n over s plus 100 n, we can just do negative 20 n plus N over S plus 100 newtons. Oh, that's T. 100 newtons divided by the mass, which is given to us, which is 5 kilograms, is equal to A of T. And if we simplify this, newtons is given by meters per second squared. So we just have negative 20 meters per second cubed, as per second, meters per second here, right? Because it's per cubed. That's my bad. Because yeah, newtons is given by meters per second squared, and if we divide that by, so multiply that by S, it becomes meters per second cubed, right? Times T plus 100 meters per second squared is not 100. I forgot to simplify this. This should be 4, and this should be 5 divided by 100. 100 divided by 5 is 20. So 20 meters per second is equal to A of T. For part D, we're asked to find or sketch the acceleration versus time. For part D, we're asked to find and sketch the acceleration versus time graph. And I'll just bring out the same graph from before. So right here, here, same graph, because basically it gives us about the same graph. So what we're gonna do is we know, well, there's two ways to do it mainly. One is to just look at this graph here, and what we know about Fn right here, Fn right here is equal to AT times 5, right? So all we have to do to find the AT graph is divide all of these values here by 5. So what we would get here is 500 divided by 5 is 20. 20, 16, 12, 8, and 4, 0. And the time doesn't change. So what we know about at t equals 0 is that newtons is 100, so we divide that by 5, which is 20 newtons. At 1 it is 80, but divide by 5 is 16. 2, 60 divided by 5, like 13, 12, and so on and so forth. So you just get the same, you get a graph that is similar in shape, right? It's just the magnitude is divided by 5. And the other way to find it is to just use the formula A of T and just plug in each value from 0 to 5, and you can just graph that. So if we use the formula here, negative 4 meters per second cubed times T plus 20 meters per second squared, we can just plug in 0. That gives us 20 meters per second squared. 1, it being 20 minus 4, so 16, 2, 12, and so on and so forth. So those are the two ways you can find it. For part E, we're asked what information can be extracted from the time acceleration versus time graph in part D. So what we can find are two things mainly, which is jerk, because the derivative of the acceleration, which is equal to the slope, right, is equal to the jerk. Jerk, which is denoted what it is. I mean, this doesn't matter. It's just a variable, right? It's a type of function. It's to derive it. But A of t, A delta A prime of t, is equal to G of t, right? The jerk. And what we know about jerk is that what we know about the derivative of a function is that it is just a slope, right? So what we know about the slope is that it is negative 20. So we just know already that jerk is equal to not negative 20, negative 4. So therefore we get jerk is equal to negative 4. And the other thing we know about, which I should write that, we know the jerk of the function or the system because the slope of A of t is given. And the other thing that we can find is velocity. And this is because the integral of A of t dt is equal to V of t. And here it will be V of t plus c. However, we are going to assume here that velocity at the start, so c, will be 0, and so will x of t. And this is done just so that the next few problems make sense and don't make it too confusing. right? So the other thing we can find is velocity. We know we can find velocity because velocity of the system, because the integral of a of t is the velocity, and the integral of a of t can be calculated by finding the area of the graph a of t, graph of a of t under the curve. Gosh, curve. And we know the jerk of the system because the slope of the a of t is I'll rewrite this actually, because we know the jerk of the system because a delta t gives us, or a derivative of t gives us the jerk, or j of t, which where a of t, a derivative of t, a t derivative of a t is just the slope of a of t. Right, so now for part F, we are asked to derive an expression for the instantaneous velocity vt. And what we stated above was that vt can be given by just the derivative, the integral of at dt. And this problem, we're gonna assume that v of c is 0, so we're just not gonna include it here. So how do they find this? Well, what we can do is just get the, well, we already know what we're gonna do, right? We're just gonna find the integral of it, which is negative 4 meters per second cubed times t plus 20 meters per second squared dt. And this just simplifies to t squared over 2, so negative 2 meters per second squared times t plus 20 meters per second t plus c. And as we stated earlier, c would just be 0, so we're just not gonna put that. And so that is our formula for the velocity function. Wait, that seems a bit weird. Meters per second. Oh, this should still be, oh, that's my bad. These two numbers should still be meters per second cubed, but t should be squared here, and that one should be just pt. Because what we know is that t is some sort of second, right? So if we multiply 20 by, like, let's say 1 second times 1 second, then these cancel out and gives us 20 meters per second. Alright, for part G, we are asked, using the known information that can be extracted from the AT graph, so this thing right here, we are asked to find the velocity at t equals 5. Right? You know, information, determine vt equals 5. So what we know about vt equals 5 is that the integral of 0 to 5 of a of t dt is equal to v of 5 minus v at 0, right? T equals 0, t equals 5. And what we can do here is rearrange this. Well, we don't even have to rearrange it, because we stated earlier that the velocity at t equals 0 is just going to be 0, because we're going to assume that. So we just have the v of 5 is equal to 0 to 5 at dt. So what is this integral? Looking at the graph, what we know about the integral is that the integral of a graph is just the area under the curve. So it's just all of this. And since it's a linear function, we can just assume we can find the area by using the triangle formula, which is 1/2 b times h, where base is 0 to 5, so 5, and height is just 0 to 20, so it's 20. So what we get is the area here, all of this, is just 50. So the integral of 0 to 5 of a of t is just 50 meters per second is equal to v of 5. And for part H, we are similarly finding v of t, but instead we're gonna v of t at 5. But instead of using using the graph here, we're gonna use a formula that we found in part F, which is just part G, which is just part F, my bad, which is just -2 is equal to -2 meters per second cubed t squared plus 20 meters per second squared. Meters per second squared and t, right? And what we can do is just plug it in now. Plug in t for all of these. This is the wrong notation. It should be like this. And if we want to find v of t at 5, we now plug in the values. Squared of 5 squared plus 20 meters per second squared times 5. This gives us negative, these should be seconds. So that gives us 25 times 2 is 50. Cancel out those two. Meters per second plus 20 times 5, which is 100. Cancel those out, gives us meters per second. And that gives us the value 50 meters per second. So at Vt equals 5, 50 meters per second. And this information agrees with the information we found in from part G, yeah. So the v of t equals 5 found in part G matches with the v of t, the Vt equals 5 found in part H. Alright, so for part I, we are asked to derive an expression for the position function. So we're trying to find x of t. And to find the x of t graph, what we know is that, well, this is very simple because we already have the velocity of t graph, and the relationship between these two is just that v of t is the integral of v of t dt is equal to x of t, right? So all we have to do is just where's the formula? So this is equal to -2 meters per second cubed t squared plus 20 meters per second squared times t dt is equal to the t becomes t cubed over 3 -2 over 3 meters per second cubed t to the third plus 20 meters per second squared t to the squared over 2 plus c. But we're gonna assume position is 0 as well here, because it makes it kind of hard later on for the next few questions. And also it never states, we're just gonna assume it's 0. So that is the formula for it, which is -0.667 meters per second cubed t to the third plus 10 meters per second squared t to the squared. And now all we have to do is now we have j. So j, we're using a graph yet again, and what we're gonna do, get the graph, wrong one, sorry, this one, and we are asked to sketch a position versus time graph on the grid from 0 to 5. So 0, 1, 2, 3, 4, 5. There's the seconds, and then we can just do 40, 80, 120, 160, and 200. And this is the y-axis is the position x m, and the x value is what is it called? The x-axis is the time, ts, given the seconds. Right, so we want to sketch the time graph and then clearly label all the axes. Alright, so let's first sketch the position time graph. So at 0, let me just use a calculator real quick. So using this formula right here, negative 0.6777 x to the third plus 10 x to the squared, x being time in the calculator. We're gonna use second table or second graph. So at 0 is still 0, but at 10 it is still 10, around 10ish, but it's smaller than that this time. At 2 is around 34, so it'll be around here. At t equals 3 it is 35, so around, oh, at 3 is 72, so around here I say. At 4 is around 117, so about here. And at 5 it is at 166, so about here. So as you can see, this is a very, it's not quadratic enough, but it is exponential at the very least, right? And now for the other parts, we actually draw a line that represents the instantaneous velocity at v equals 2, which is, we're just gonna estimate it. It says to just draw a line that represents it. It doesn't have to be accurate, so we'll just draw a line, a slope that's tangential to the slope at vt equals 2, or not vt equals 2, at xt equals 2. And then for the second part, we're asked to draw a line that represents the average speed from 0 to 1. So average speed from 0 to 1 is like that. From 0 to 2, like this. 0 to 3, 0 to 4. I'll use a straight line. 0 to 1, 0 to 2, 0 to 3, 0 to 4, and 0 to 5. And we are asked to clearly explain what happens to the average speed of the car during each interval. All right, for each interval, we can quickly just find the average speed, like here, right here, right here, because average speed is given by delta x over delta t, right? So we're just finding at each second, so 0 to 1, it goes. The displacement is just this amount from here to here, and then the t is just the time, right? So each slope is like this. But as we can see here, it is increasing every time. It's become slightly, at the very least, more steeper from each second. So what happens to the average speed average of the car during each second is that it increases. Okay, so I'll write it here. The speed, average speed of the car during each second interval during the window t equals 0 to t equals 5. The average speed is increasing from each time interval as the slope at each interval becomes steeper. And we can also prove this using math, because all we have to do is find the time, the position at 5 and position at 4. So t at 5, x at 5 minus x at 4 over 5 minus 4, right? And I'll just find this really quickly, because I do have the table. So x at 5 is given 166.67. X at 4, 117.33 over 1 is 166.67 minus 117.33. 53. That gives us 49.64. And we'll just find the x of 4 minus x of 3, or 4 minus 3 is equal to 4117 minus 72 over 1. 7.33 minus 72, and that gives us 45.33. So we proved it both mathematically and by looking at the graph. I won't write it down though, because I'm kind of lazy. Alright, for K, we're asked to calculate the average velocity between t equals 1 to 3. So average velocity, v average, on speed, is given by delta x over delta t. And this is in a, what would you call it? In the delta, when you're trying to find speed, it'd be absolute value and whatnot. It would, it wouldn't be delta x, it'd be d for speed, but whatever. I don't know why I'm talking about that. Well, anyways, v average is given by delta x over delta t. And what we know about delta x, we can just rewrite this as delta, not delta, at x of t final, we'll just use f here, xtf minus x of t initial denoted by I, and we can do tf minus ti. And since we're trying to find the average velocity between t equals 1 to 3, we can just put the final time as x of, so v average from t equals 1 to 3 will be given by x at 3 minus x at 1, 3 seconds, and x at 1 second, 3s minus 1s. And I still have the formula in my graphing calculator, so I'm just going to use that. And at x of 3 is given to us as 72, and x of 1 given to us by 9.33, and 3 minus 1, and that simplifies to 62.667 over 2. And oh, I should write this down. Meters, second. So this is what we're left with, and it is just 31.33 meters per second in the positive x direction. And that's it for this video. Have a great rest of your day.